Okay, so welcome back to another session. I hope you're all doing great. So as you well know, today is a reading day. As I told you on Monday, you didn't have to be in class today, but if you want to join me to record this, that's fine, right? But everyone is required to watch this. I'm going to teach today, right? Everyone is required to watch this. The content here are very, very important. Okay, so with that said, let me get on to recording this. Today, we are going to continue from where we left off. The last time I talked to you guys, we were looking at the chain rule. So let me just go and share my screen and continue from where we left off. Share screen. Okay, let me see. Okay, at least you guys are there. But if you can't see, for those on, if you can't see my desktop, do let me know. Okay, so the last thing we did before we went away on Monday was we tried to prove the chain rule, right? So we obtained the proof. As I told you, the proof is not something I'm going to ask you to do, right? But it's a good idea to see it. And for some of you to be important moving forward, you may have to know how to derive it because you'll be dealing with proofs later on in your coursework, right? So we did the proof. Now the proof led to this conclusion. We said that whenever you're trying to find a derivative, right, and then the function you're differentiating is a composite function. What we mean by a composite function is it's a function inserted into another function, right? A function in a function. Now, if you're able to see that to be a composition, then in order to get a derivative, right? So the derivative of a composition, right, where we have an outer and then an inner. So you're plugging an inner in some outer function. Then this derivative is just differentiate the outer function, plug in the inner function, and then multiply by the derivative of the inner function, right? Now, this thing that you guys see here is like a product of two separate derivatives. So whenever you have a composition, let's say two levels, and you differentiate, like there's an outer function and some inner function. When you apply the derivative, you end up with multiplying two separate derivatives, which is f prime and then plug in j of s and then j prime. Now those two derivatives will be multiplying. So you can liken this to like a link in a chain. A link in a chain, right? Because when you have a chain, then a chain is just made up of links. So it gets its name as a chain rule because you end up multiplying derivatives. So the derivatives are like links. So that's why it's called a chain rule. So you'll be multiplying what? You end up multiplying derivatives. So that's where it gets its name from, the chain rule. So the derivatives are links multiplying together. So they form a chain, right? So that's the chain rule. Okay, so we've already shown this proof, right? And then I said that the chain rule can be written in prime notation. And that's the one we are going to use in this class, right? So in prime notation, if you have a composition and trying to get a derivative, differentiate the outer function, plug in the inner function, times the derivative of the inner function. So you can do it this way, right? Or you can use Leibniz notation. Now, for all of these, I'll show you how we are going to apply it in an example, but I won't be using the Leibniz notation going forward. It's just for knowledge purposes. It's part of the content. You have to know, but you won't be using the Leibniz notation. You'll be using the prime notation for this class. So in Leibniz notation, all that you're going to do is just let u be the inner function, right? Remember that the composite function is given by f g of x, right? This is a composite function. Yeah, so that means with this one, this is the outer and that's the inner function. So what the Leibniz notation is saying is just let u be equal to the inner function, right? So set u equal to the inner function. Now, if you set u equal to the inner function, then your original function becomes f of u, right? Your original function becomes f of u. And then you have this. So if you want to get a derivative, just this function is now going to be a function of u. So you can just get dy du. So that's this. And then this function will just be u equal to g of x. So the u will be the dependent variable, and then the s will be the independent for this second case, right? For this second function. And then that one, you can get du over dx, right? And when you're done, you can multiply them together, and then you end up substituting the u back in, and then you get your dy dx. I'll show you how this is applied in an example, right? Please, I hope you're okay up to this point, since there are a couple of you on. Okay, so now let's try and use the chain rule to what? To get this, to get an answer to this, right? So let's work this. I'm going to do this on a whiteboard. So That's 3.4 example 1 on slides. Okay, so the example says find f prime of x if f of x is equal to what? Square root of s squared plus 1. Okay, so to find this, let's go through the normal procedure that we use. So solution. So we start by, where's my time? My timer. Okay, I don't see it. Oh, okay, it's over there. Okay, don't worry, I'll use a different way to check the time. So we start with what? Writing this out. So we have f prime of x. So if the f of s is given by this, then the f prime is just what? Attach the differentiation operator to the function. So we have square root of s squared plus 1. And then when you attach this differentiation operator, you start asking yourself, do I have a direct derivative rule for this? Now, going through all the rules we've learned, there is no direct rule for this, right? It's not like something like an e to the x where the derivative is just e to the x. No, that's not it. It's not like a constant where it's direct. Okay, so you have to be thinking about some other thing. Is it a sum of functions, a difference of functions, or what? Is it a product of functions? Well, this is not a sum of functions directly. It is not a difference of it's not a difference of functions directly. It's not necessarily a product of functions, but what can we do? Oh, but let me write this as so. S squared plus 1 all to the half. Now, if I write it this way, then I can see, oh, this one I can consider it to be what? A composition. This can be seen as a composite function where my inner function is s squared plus 1, and then my outer function is something to the power half, right? So let me show you this. So note that if f of x is equal to s to the half, how you decompose this? And then g of x is equal to what? S squared plus 1. Then f of g of x, which is a composite function formed out of these, will be what? Will be s squared plus 1 all to the half. So that's what I mean. So when you look at the function, you should be able to identify that it's a composite function, right? Now, after identifying it's a composite function, figure out your inner function and what your outer function will look like. You see, so in this case, I'm just writing this out because it's one of the first examples we're looking at, right? So decompose. If I decompose, it makes sense that if my outer function is s to the power half and my inner function is s squared plus 1, then the composition f of g, f composed with g, will be given by what? S squared plus 1 all to the half, which is the same as the expression we have here, right? So if I'm able to figure that out, then I do this. So, okay, so because it's a composite function, which rule am I going to use? I'm going to use the what? The chain rule. So what does the chain rule say? The chain rule says whenever you have a composite function, differentiate the outer function. So in this case, looking at this s squared plus 1 to the power half, my outer function is what? S to the half, right? So if you're differentiating x to the half, what do you do? Well, that one you can employ the power rule. So by the power rule, bring the exponent down, and then I would have normally written x and then subtract 1 from the power. But we don't write the x here. We have to plug in the inner function. So I can't put in x here. That's why usually I just do the parentheses without putting anything in there, right? So normally it's half x to the power half minus 1. But we have to plug in the inner function. So that means that I can put x here. I'll have to put what? The inner function. What's that? That's s squared plus 1, right? So that would be the first link of the chain. Now, the next link will be what? Multiply by the derivative of the inner function. So that means just do the derivative of the what? Of the inner function, which is s squared plus 1, like so. So you have it set up now. Then you just focus on where the differentiation operator is. It's attached to what? D over dx and then s squared plus 1. Now for this one, let me write this. Let me make this note here. Let me say this one is using prime notation. Using prime notation. I'll show the Leibniz notation here on this example, and that'll be it, right? So this is the prime notation. Okay, so using the prime notation and continuing, we are looking at this part, right? So for this side, I can just simplify this. This half s squared plus 1 to the negative 1/2, and then the derivative of this function. Now this is just going to be what? Differentiate the sum rule. So differentiate the s squared. That's going to be just 2x, right? And then the derivative of 1 is 0. Now, on an exam or in your homework or anywhere, you can just leave your answer like this and you are done. But if you want to, you can simplify further, right? This is okay. You can type this in WebAssign to accept it, but you can also simplify further if you want. So that'll be the 2's will cancel out. Then I have x over square root of s squared plus 1. Yeah. Oh, where did I get? Okay. So where did I get a 2x from? So Taylor, do you see that I've been able to use the chain rule to get this term and then that one? You see that, right? You understand up to this step. Do you understand up to this step, this setup? Okay, perfect. So when I got here, right, the differentiation operator is attached to the s squared plus 1, right? So I just focus on this side, focus on getting the derivative for this side. This side, there's no differentiation operator attached, right? I'm just looking at this. And then I got the 2x from what? The derivative of this sum. So this s squared plus 1. So what's the derivative? You do the sum rule. So you differentiate it term by term. And the derivative of s squared is 2x. The derivative of 1 is 0. That's how come I got the 2x here. Please, does it make sense now? Are you okay? Perfect. Okay. So that's it. Right. Now, let me use the other approach. Let me use Leibniz notation. Using Leibniz notation. As I said, I won't be doing this going forward. I'll be using the prime notation because that one is easier to implement. Okay. So using the Leibniz notation. So first, for the Leibniz notation, we just have to set the inner function to equal to what? U. So we have f of x equal to what? Square root of s squared plus 1. So how do you get the derivative? Well, assume this is y. So let y be this. Assume this is y, right? So that means in this case, we let u, which is the inner function, u be the inner function. So that's this, right? So if u is equal to s squared plus 1, then what is the original function? Well, the original function will be y equal to square root of u, right? So now the initial function will no longer be a function in terms of it. It will just be in terms of u, right? So we have y equal to square root of u, and then u equal to the inner function, which is s squared plus 1, right? Okay, please, anybody needs time here? Okay. Come on. Okay, so then moving forward, let's see. So by Leibniz notation, our dy, don't forget that the independent variable in the original expression is x. So we're looking for dy dx, right? So our dy over dx will be equal to what? Well, we can do dy over du times du over dx, right? That's what Leibniz notation says, right? So we can do dy over du because the new y function we have is now in terms of u. So that'll just be, so let's do dy over du. So dy over du will just be equal to your d over du of what? Square root of u. And what is that? So that's d over du of what? U to the power 1/2. And then that will be the power function. So that will be half u to the half minus 1. Right. So that's it. Now let's get the other piece, du over dx. What is du over dx? You just attach the differentiation operator to what? To the u function. What is that? That is s squared plus 1. So that's s squared plus 1, like so. And then you differentiate. So for this one, it will be a sum rule. So by the sum rule, differentiate it term by term. That the first one give you 2x, and then the next one give you 0. So that's 2x. Now the final thing is, it's too much room here. Let me create. Yeah, so the final thing is we have dy over dx equal to what? Dy over du, what's that? That's half u to the what? Half minus 1. And then times what? Du over ds, what is that? That's 2x. So I just do 2x. But then the original equation, the original function you were given was in terms of x, not u. So you have to substitute the u back in it, right? The u is what? S squared plus 1. The u is s squared plus 1 from here. The u is s squared plus 1. So you have to put it back in x. So we have half s squared plus 1. Let me subtract the power here. It's just negative half, and then times 2x. Now, these also cancel out and simplify. I mean, you are right if you leave your answer here, right? After substituting the u back, this is perfectly correct. But you can also simplify if you want. But please, on the exam, please and please, because our time is just 15 minutes and it's short, please don't focus too much on simplifying, right? When you get your dairy, just type it in. Don't spend too much time trying to simplify to the barest, the barest like possible simplification. No, immediately you get your answer, just type it in. It will accept it if it's correct. Yeah, that's it. Unless maybe it's an equation of a tangent line or something. Yeah, so that's it. That's our answer. And even with this, you can even write it as s squared of s squared plus 1. Yeah, that's why I said don't focus too much on simplifying. Yeah. Please, any questions here? So that's Leibniz notation. I'm showing this because of knowledge purposes, that so that you know there is something like this. But you'll be using prime notation. As you can see, with the Leibniz notation, we work more steps. The prime notation is more direct, right? So that's why you're going to use that. Please, any questions so far? Okay. Anybody needs time here? Okay. Then let's just go to the PowerPoint. Okay, so I'm sharing the PowerPoint now. So this just gives us nice news, right? So it says using equation 2, and what's that one? That one is, oh, way back. I'm not sure where this is. But still, oh yeah, this is the function. This is the prime notation. So this is equation 2, using f prime, the prime notation, right? So this is the first one, solution 1, right? So using prime notation. I wonder why it even used the u here. It's as if it's mixing the prime notation and the Leibniz notation. But still, yeah, the prime notation is direct. So we have this, right? So just look at this, right? So if you want the derivative of a composite function, differentiate the outer function, plug in the inner function, times differentiate the inner function. Well, to help you really grasp this, I think I have some interesting, let me see, desktop. No, that one is documents. Some interesting way. I saw this on, yeah. Please, can you see my screen? Can you guys see my screen? Oh no. Guys, are you there? Can you see I'm sharing a photo. I'm sharing a photo. Can you see it?
Yeah, I can see it.
Let me see. So one way some guy says he used to remember this is it's kind of like a pregnant lady, right? A pregnant lady. So if you're differentiating the pregnant lady, there's a kid in her belly, right? So differentiate the mother, leave the baby inside, times differentiate the baby. Kind of, yeah, kind of like funny when you think about it, but it works if it helps you to memorize this. Yeah. So if you have composite functions like a mother with a baby in there, right? So differentiate the mother, leave the baby inside, times or differentiate the baby, right? So that's the chain rule. So if it helps, okay. As I said, it's on you guys to memorize these things. So I just try to give you some tips on how to memorize it if it works for you. Yeah. So that's it on this. Please, any questions so far? So that's solution 1, and then they use the Leibniz notation. Okay. Now, any questions? Okay. So now let's look at, so right now, the main challenge is to be able to figure out which one is your inner function and what's your outer function. So here we're looking at something like a case whereby the outer function involves a trig function, right? So when you have y equal to sine of u, where the u is another function, right? So for trig function, the outer function is always like so. Like if you have it like this, then the inner function will be here. Well, one other way to identify what the inner function is, think about it in this sense. If you are going to compute values for the given function, which one will you compute first? So if I give you something like sine of s squared plus 1, and I ask you to evaluate x at 1, what will you do? What will you do first? You first compute this before you apply the sign on it, or unless you are typing it straight for it. But if you're doing it step by step, you first deal with this one first. Let's say you have a calculator which doesn't take everything at a go. Then you have to do this first before you do the sign. So that's how you know this is your inner function. Or you can also train yourself, and with experience, you see where to identify the inner function. So when it involves something like the sign of something, then that thing is always the inner function. And then the sign will play the role of the outer function. Okay. So for that one, you know that if you're doing the d over ds of sine of u, where u is another function which we can differentiate, then by the chain rule, differentiate the outer function, which is sine, and then the derivative of the outer function is cosine. But then you plug in the inner function, right? Leave the baby inside. So you have to leave the u inside. Multiply by what? The derivative of what? Multiply by differentiate the baby, right? So differentiate u. That's what you have here. Okay, so that's trig function. And then they combine with the chain rule. Okay, so now let's try and work some examples here. For this one, we can work it on since the solution is not here on the PowerPoint. So this one says differentiate this. So for A, I go, okay, y prime. That's what I need, right? So attach the differentiation operator, sine of s squared. And then you ask yourself, do I have a direct differentiation rule for sine of s squared? No, we don't. We have the derivative for sine of s, but not for sine of s squared. Okay, then let's run through the questions. Is this a product of functions directly? No, not really. Is it a sum of functions? No. Difference? No. Oh, wait. This can be seen as a composition where this is my outer and this is my what? Inner function. Immediately, I'm able to identify that it's directly a composition, right? It's a composition in itself. Then I can employ the what? The chain rule. So what does chain rule says? Differentiate the mother. In other words, differentiate the outer function, right? Sine. What's the derivative of sine? Cosine. Keep the baby in there, right? So put in the inner function times the derivative of the inner function. And then after this step, I just focus on this part, right? So the derivative of cos s squared is what? It's just 2x by the power rule. So I'm done. That's my answer. So 2s cosine of s squared. And that's all. Please, any questions on this? I hope it makes sense. Okay. So now let's look at the B. For the B, we need y prime. So that'll just be attach the differentiation operator to it. You have sine squared x. And then we ask ourselves, is this a, do you have a direct rule for this? No, we don't. Well, for this one, you actually have, I think I see at least two ways you can do this. You can look at this as a product, right? Because sine squared x is the same as sine of x times or sine of x. And then you employ the product rule. But since you're dealing with a chain rule here, I would like to use a chain rule approach, right? But you're not going to be wrong if you use a product rule. So I want to see this as a chain, as a composite function. So I can rewrite sine squared x as this. So if I rewrite it like this, then it's as if the sine is what? It's my inner function. And my outer function is a power function. So by the chain rule, what will we do? Differentiate the outer function, right? So that's 2. Plug in the inner function. So repeat the sine of x here. And then by the power rule, you have to subtract 1 from the power. Multiply by the derivative of what? So the derivative of the inner function. So that's the derivative of sine of x. So putting everything together, this side will just be sine of 2 minus 1 is 1. So that'll be just 2 sine x. And then you differentiate the inner function. The derivative of sine is what? Is cosine. So that's it. That'll be your answer. And you get the same thing if you use a product rule, which is something which will be good for you guys to check if you are interested. Yeah. Please, any questions on this? The chain rule is one of the most useful techniques you ever learn. Yeah. Anybody needs time here. Okay. Now, let's look at the chain rule combined with the power rule, right? When you combine the power rule and the chain rule, what happens? So for that one, you have some differentiable function u, and then that one is to the power n, right? So when you do this, what do you do? Well, we've seen a couple of this way back, right? So I think, let me show you using this. So if you have a function g of s here, all to a power n, where the n is a real number, then you can employ the power rule as follows. So just bring the power in front, subtract 1. But we must plug in the what? The inner function. You have to keep the baby inside, right? You have to keep the baby inside. So you put it in. Instead of writing x there, right? You don't put x there. You have to put the baby in there, right? So the baby here is g of s. So just put g of s back in here. And then when you're done, you have to what? Multiply by the derivative of the inner function. So that's why we have times of j prime of x. Okay. So that's combining power rule with chain rule, which we've seen a couple of examples. Please, any questions here? Okay. Anybody needs time here? Okay. So this is an example of the power rule combined with the chain rule. So you have to differentiate this, right? Now I've been doing a couple of these. So guys, let me see. Do you want to try this? I mean, today is reading day. If you don't want to try, that's okay. But I would like it if you guys can see if you understand this. Do you want to try this? Okay, let me just give you a minute or some seconds to see if you can try. If I don't get any response, I'll just work this out. Yeah, so please try this. Differentiate this and let's see. I'll give you some seconds. Or if someone is working it, just voice it out and let me know. Let me know if you're working. Or if you're not interested, I can also do it. That's fine. Today's reading day. You guys are supposed to be resting a bit, so no stress. No one is doing it. Okay. Okay. So if no one is doing it, then let me just do it. I think the solution is on here. So let me just go to the whiteboard. This is example 3. Okay, so example 3, we have y equal to what? S cubed minus 1 to the 100, right? And then we are asked to differentiate. So what do we do? Well, we need y prime. So just attach the differentiation operator to the s cubed minus 1 to the 100. And then we go, okay, so, well, this one is, we can see this to be a composite function, where our inner function is this, and then our outer is some power function. So what do we do? Well, by the chain rule, you differentiate the outer function. So bring the 100 in front, and then x, this time I won't write the x because I'll be plugging in the inner function, and then subtract 1 from the power. So the x is what? S cubed minus 1. Multiply by the derivative of the inner function, which is s cubed minus 1, like so. And then the rest is to just focus on this second piece, right? Derivative of s cubed minus 1. So that's 100 s cubed minus 1. 100 minus 1 is 99, right? And the derivative of s cubed minus 1 is just 3s squared. So that's my final answer. So I have something like 300 s squared and then s cubed minus 1 to the 99. And that's my final. Okay. Anybody needs time here? Any questions on how I obtain it? Okay. Then let me go back to the PowerPoint. So this is just going to show us the solution, right? So we know that your inner function is s cubed minus 1, and then your outer function is like x to the power 100. So by the chain rule, differentiate the outer function. The outer function, how do you differentiate the power function? By the power rule, bring the power in front, subtract 1 from the power. But then we can't write x there. We have to plug in the inner function. So that's how can we see not x to the power 99, but rather 100 s cubed minus 1 to the 99. But then when you are done with that, that's not it, right? You have to multiply by the derivative of the inner function, which is very, very important, right? So differentiating this, you have to do what? This is the difference rule. So you differentiate s cubed, differentiate 1. The derivative of s cubed is 3s squared. The derivative of 1 is 0. So you get this. Then you can simplify it a bit. But the Weber sign will accept it if you give it this answer, right? Okay. So now let's do more examples. So example 4, let me see. Is this one has an, oh, it doesn't have a solution. Yeah. So for example 4, let's do it together. So for this one, I'm asked to find the derivative, right? So I need f prime. So what is f prime? Well, just attach the differentiation operator. Here, the independent variable is x. So we are doing d over dx, right? And then 1 over cube root of s squared plus x plus 1. Okay. So now for this one, it looks like a quotient. So we can perhaps employ the quotient rule. That will work all the same. But a much easier route to go would be to rewrite this expression as, you know that this is the same as 1 over, if you have a cube root, is the same as 1 over 3, power 1 over 3. And then still we can do more, right? We can do more. Now that one is the same as s squared plus x plus 1 all to the power negative 1 over 3. Okay, so now this is a structure I need, right, to make my life way easier to get this derivative. So I asked myself, okay, do I have a direct derivative for this? No, we don't have a direct derivative for this. It's not like a standard e to the x kind of thing that you can easily get it straightforward as e to the x, or like some power function which you can easily get it, right? This one is something else. Okay, but then what we should be thinking, if it's something else, is it a sum, difference, a product of some functions, or what? Well, this one is not directly a product. It's none of those, but we can see this to be a composite function, right? Where my inner function is here, and then my outer function is this power function. So immediately I'm able to identify that, then I know I'm going to use the what? The chain rule. So by the chain rule, you differentiate the outer function. The outer function is the power function. So how do you differentiate the power function? Well, you bring the power in front. And the normal circumstance, if it was x to the negative 1 over 3, you would have written the x here. But here, the base is not x, right? The inner function has to be plugged in here. So instead of x, you have to plug in the inner function. And then subtract 1 from the power times the derivative of the inner function. Please don't forget that piece, like so. Right? And then when you are here, you're going to get negative 1 over 3 s squared plus x plus 1. The negative 1 over 3 minus 1, that's just negative 4 over 3. And then what about this derivative? Well, for this one, we can employ the sum rule, right? So put everything in parentheses and differentiate them term by term. The derivative of s squared is 2x. The derivative of x is 1. The derivative of 1 is 0. So that's our final answer. And you can simplify if you want, but as I said, please don't spend too much time simplifying. When we get to chapter 4, you'll be doing more simplifications because at that place, it will be needed. You must do the simplification to get it. Yeah. And that's all on this. Please, any questions here? Any step you don't understand? Anybody needs time? Okay. Then let's move on here. So now this is just more examples, right? So here we're giving g of t equal to this t minus 2 over t 2t plus 1, all in parentheses to the 9th power. So let's find g prime of t. So in this case, the independent variable here is t. So we have to do d over dt, right? Of what's the expression? So here's t minus 2 over 2t plus 1, all to the 9. So we run over the questions again. Is there a direct derivative for this? No, we don't. We don't have a direct one. Okay, how can I see this to be? Well, this has a quotient in there somewhere, but the function itself is not directly a quotient. Well, unless you write it as t minus 2 to the 9 or divided by 2t plus 1 to the 9, then you have it as a quotient, right? And that will make my life easier. What I can do here is I can see this to be some composite function, right? This is my inner function. The inner function is just that t minus 2 over 2t plus 1. And then I can also see this as my outer function. So in that sense, I've been able to see this whole function as what? As a composite function, right? So immediately I identify my inner function and my outer function. That means I can employ the chain rule. So what does the chain rule says? It says differentiate the outer function, which in this case will be the power function. So bring the 9 in front, subtract 1 from the 9, right? But you have to plug in the inner function. So 2t plus 1, then subtract 1, times the derivative of the what? The inner function. The inner function happens to be t minus 2, 2t plus 1. All of this. Okay. Then moving on, we just focus on the second piece. So that's 9 t minus 2 over 2t plus 1. And then that's 9 minus 1 is 8. And then this derivative, we can use the quotient rule now, right? So by the quotient rule, what's the rule? Low d high minus high d low over square of what is b low. So what is low? Low is 2t plus 1. D high, the derivative of t minus 2 is just 1. Minus high, t minus 2. D low, the derivative of 2t plus 1 is just 2. Over square of what is b low. So that's 2t plus 1 all squared. And that's our final answer. You can simplify if you want, but Weber-San will accept this, and I will also accept this. Okay, so that's it for this. Any questions here? Anybody needs time? Okay. Now let's look at another one. Another example, more example. So let's look at this one. Let's differentiate this function. So the solution. So for this, we need y prime. So just attach the differentiation operator. Here, the independent variable is x. So we just do over dx. And the expression is 2x plus 1 to the 5, s cubed minus x plus 1 to the 4. Okay, now let's start thinking about this expression we have here. The question is, the 2x plus 1 to the 5 and then the s cubed minus x plus 1 to the 4. Do you have a direct derivative for this? No, we don't. Well, is this a composition? Well, this is not straightforward a composition. This is rather a product of two composite functions. You see, so it's not directly a composition. It's a product of compositions. So it's a product first and a composition next, right? So you have to employ the what? Since it's a product, we employ the product rule. So by the product rule, leave the first one alone, multiply by the derivative of the second, plus what? Leave the second one, multiply by the derivative of the first. So you have to employ the product rule first, right? Because the function as a whole is not directly a composite function, right? So now that we've broken it up, we look at where the differentiation operators are attached and then try and get those, right? But then now looking at this first piece, where the differentiation operator is attached on the first part, we have d over dx of what? S cubed minus x plus 1 all to the 4. That one is a composition, right? Where my inner function is this, and then my outer is 4. So I have to employ the chain rule on that expression. So by the chain rule, differentiate the outer function, and that will be the power function. So that's 4. Plug in the inner function. So 4 minus 1 for the power function, the outer function, right? And plug in the inner function. Multiply by what? The derivative of the inner function. Another one. And then plus, let's look at the other one, the other piece. So for this one too, you have s cubed minus x. No, wait. Yeah, we have to leave that one alone because the differentiation operator is not attached. And then we do this one. For this one too, we have a composite function where our inner is 2x plus 1. Then our outer is another power function. So by the chain rule, differentiate the outer function. So you bring 5 here. Plug in the inner function. So we have to do 5 minus 1 because we're doing the derivative of the outer function, which is the power function. And then times the derivative of the inner function. Here, the derivative of the inner function is more direct, right? The derivative of, okay, let me just write it here. So that's 2x plus 1. And then next, this is the last line. We have 2x plus 1 to the 5 times 4, and then s cubed minus x plus 1. 4 minus 1 is 3. Now let's do the derivative of s cubed minus x plus 1. You do it term by term, right? Because it's a difference and sum. So derivative of s cubed is what? It's 3s squared. Derivative of x is 1, so we have minus 1. Derivative of 1 is 0. So that's it for this first part. Now for the next part, we have s cubed minus x plus 1 to the 4 times 5. And then this one is just 2s plus 1 to the 4. And then the derivative of 2s plus 1 is just 2. So that's our final answer. And you can type this thing in. Weber-San will accept it. I'll also accept it if you come on the exam. Okay. Please, any questions here? Yeah. So this is where we apply the product rule before we employ the chain rule. No one needs time. Okay, then let me move on. Now let's do more examples. So for this one, we have to differentiate another example, example 7, right? We have to differentiate this e to the sine of x. So we have y prime d over dx of what? E to the sine of x. So you ask yourself, is there a direct derivative for this? Well, the closest I can see is e to the x, but this is not e to the x, but this is e to the sine of x, right? And for power functions, their inner functions are always in the power, right? So that means let me write this on the side. It's as if you have something like, say, f of s equal to e to the x, and then g of s is equal to what? Is equal to sine of x. If I ask you to get f composed with g, then it's just going to be e to the sine of x. You see? So that's what's happening here. So for this power function, the sine is our inner, and then e to the x kind of thing is our outer, right? So the e is our outer function. So immediately identify those. You use the word, this is a composite function. So you can use the word, the chain rule. So by the chain rule, differentiate the outer function. So what's the derivative of e to the x? It's just the same e to the x. But we can't write x there. We can't write e to the x. You have to plug in the inner function. So you have to do what? E to the sine of x times the derivative of the what? The inner function. Derivative of sine of x. Right? So that means you are going to be left with e to the sine of x. The derivative of sine of x is cosine. And that's it. Now we don't have any differentiation operator, so we know we are done. And that's our final answer. Please, are you okay on this? Any part you don't understand that you want me to go over? Okay. Anybody needs time here? Okay. Now let's do more. So another example. So for this one, we have f of x equal to sine of cosine of tan of x. This one is like nested functions, right? It's like 3 in 1, right? So you have tan of s, put in a cosine of x, which is also put in, I wish I had like a third, like I can push it in. Yeah, push it another function. Do you see? So this is an inner function, which is also a composite function. So how do you do that, right? So solution. So a side note, right? Just note, if you have f of g of g of h of x, right? If you're trying to find the derivative, then it's still the same idea. The f is your first outer function, so you have to differentiate your outer function, plug in the inner function. So that'll be g of h of x times what? The derivative of the inner function. So the inner function is also a composite function, like so. So that one you employ the what? The chain rule. So you end up having f prime g of h of x. Okay, you have 1, 2, 1, yeah. And times, for this one, you employ the chain rule. So differentiate the outer function. This time to be j prime. Plug in the inner function times the derivative of the inner function. And then you're finally done. So the number of nests that you have, nested functions, you always keep going until you get to the very inner function, the derivative of that, the very inner function, right? So that's why, as I said, it's called a chain rule. It will end up being like a product of derivatives. So they are like links in a chain. So f prime of g h of x is one link. J prime of h of x is another link. H prime of x is also another link. So imagine you're doing it for several nested functions, like 10. That means you end up forming like 10 links. And that's like a chain, you see? That's why it's called a chain rule. Okay, so that was just a side note. So for this one, let's get the derivative. So you just attach d over dx to sine, cosine, tan, like so. And then you say, okay, so for this function, we don't have a direct derivative. It's not a sum, it's not a difference of functions, but it's a composite function where my outer function is sine, and then my inner function is the whole of this. So I employ the what? The chain rule. So by the chain rule, differentiate the outer function. So what's the derivative of sine? That's cosine. Plug in the inner function. Plug in the inner function. So that'd be cosine tan of x times the derivative of the inner function. That'd be cosine tan of x. And then you just ignore the first piece and then focus on where the differentiation operator is attached, right? So I just repeat the cosine of tan of x, right? And then the derivative of cosine tan of x. So that one is also a composite function where my outer is cosine, and then my inner is tan. So what's the derivative of cosine? That one is negative sign. So let me put this in point. That's negative. No, let me use. So that's negative sign. Plug in the inner. Tan of x times the derivative of what? The inner. And what's the derivative of tan of x? That's secant squared. Right? Secant squared of x. So maybe let me bring the negative in front here so that it takes care of this one. So sine of tan of x. And then this time secant squared. And that's it. That's your derivative. Okay. Please, any questions here? Yeah, so it's good we at least saw it for three levels. Okay. Anybody needs time here? Is there any part you don't understand that you want me to go over? Okay. Oh, another example. Wow, this has a lot. Okay, so now let's get the derivative. So solution. So you're doing y prime. So that just be d over dx of what? E to the secant of 3 theta. So as you saw in the previous example, when you have e to the x of some or e to the something, that upper function is your inner function, and then e is your outer. So you have to employ the chain rule. So by the chain rule, differentiate the outer function. The derivative of e to the s is still e to the s. In this case, e to the theta. Oh, wait, I made a mistake. It's theta here, so I have to do d over the theta, not dx. Right. Okay, so d over the theta. Yeah, like so. Okay, so now with this one, you differentiate with respect to theta, right? If you differentiate the outer function, it's still e to the same thing, right? So just plug it in, secant of 3 theta. And then times what? The derivative of the inner function, which is secant of what? 3 theta. Now, it turns out that this one is also like 3 nested function because we don't have the derivative of secant directly, secant of 3 theta directly. We have the derivative of secant of theta. But in this case, what's inside here is also another function by itself. So this is an inner function. This is our outer. So you have to employ the chain rule on this. So it's like 3 levels, right? So I just repeat this, secant of 3 theta times. So what the derivative of secant of secant of say x, right? That will be secant x tangent x. But in this case, you have to plug in the inner function. So it will be secant 3 theta tangent 3 theta. Don't forget, it's supposed to be like the derivative of say theta. The derivative of secant of theta is secant theta tangent theta. But you have to plug the inner function 3 theta in there. That's how come I have secant 3 theta tangent 3 theta. Right. And then I'm not done. I have to multiply by what? The derivative of the inner function. And then finally, I have this e to the secant of 3 theta times secant 3 theta tangent 3 theta. And the derivative of 3 theta, that one is easy. It's just 3. So that's it. I'm done. Okay. Any questions here? Okay. Anybody needs time? Okay. Now let's come here. Now, we are now going to learn another new rule, which is the derivative of an exponential function. When we looked at an exponential function in the past, we just did it for the derivative of e to the x. But now we're going to do it for a general b to the x. So for this, let me just show you. I don't want to use this to show you. Let me show you for a general. So suppose y equal to b to the x. What is this derivative? Y prime equal to what? Maybe after this, then I'll just end the class this time. Then you guys should watch this recording. So y prime will just be okay. Or should I end? Yeah, let me end here. It's 50. It's 50. Okay, let me end here. Yeah. So I'll continue on Friday. So see you guys on Friday. Yeah. All the best.